Today I'm going to do a video on like finding the systems of equation solution to matrices to differential equations using matrices. And I made a video a second ago that included some more stuff, but I'm redoing it. So for this one we're going to go straight to solving. We have x prime of t. Our x prime vector, or is equal to a x vector. For this example, I'm going to use a is equal to 1, 2, 2, 1. So the first step to solve this is we're going to have to find the eigenvectors. Eigenvalues, I mean, sorry. So to find the eigenvalues, let's talk about the eigenvalues and what they are. So we have a times c is equal to lambda c. So A is a square matrix. So that's our square matrix. And then we have lambda here is our eigenvalue. And then c is our eigenvector. So we have our eigenvalue. We have to make sure that the eigenvector is not 0, because otherwise everything would zero out. That would suck. The eigenvalue is, a number for which we get our square matrix from our eigenvector. So AC minus lambda c equals 0. And so we ended up with, taking out the c, we have a minus lambda c equals 0. And so when to solve the, matrix solution, we take the determinant. I'm going to use, this inside bit here. So we have a minus lambda, with the determinant of that equals 0. So that's to find lambda. And then c, I'm going to use a nu later on to represent that. I use nu. C is our eigenvector, so we're going to find the eigenvectors, and then with the lambda and the eigenvector, with the eigenvalue and the eigenvector, we can solve the equation. So for my example, I'll just pull it up again. So A is 1, 2, 2, 1. So the determinant of right. So we can't just subtract a minus lambda, because lambda is a vector and a is a matrix. So in order to do that, we're going to convert it. So we're going to have a minus I lambda, or lambda I, where in is an appropriately sized identity matrix. And so if you think about it, when we multiply in lambda times our identity matrix, we just convert it into a matrix of the right size, and then we can subtract them. So it's a to the n. So we can have this matrix, or this identity matrix. They get bigger. It just follows that pattern with the diagonal one. So taking the determinant, we have determinant of a minus lambda I. We're going to end up with 1 minus lambda, 2, 2, and then 1 minus lambda again, which equals 1 minus lambda 1 minus lambda minus 4, because we add these, and then we subtract these, is equal to 0. So we want to solve that. And this is just algebra now. So we have 1 minus 2 lambda plus lambda squared minus 4 equals 0. So lambda squared minus 2 lambda minus 3 equals 0. So our product is -3 and our sum is -2. And so we have
Come in.
yeah,
Use this.
Yeah.
Sorry, man. You're using the kitchen.
minus 3 lambda minus 3, and then lambda plus 1 equals 0. So lambda is going to be -1 and 3. So those are our eigenvalues. So now we have the eigenvalues for those. So I get lambda 1 equals -1. Lambda 2 is 3. And so now we're going to, now we have step 2. So for step 2, we're going to find our eigenvectors. So we're going to plug in our lambdas. So plugging in lambda 1 equals -1. We have this. We have so 1 minus -1, 2, 2, and then 1 minus -1 times, I'm going to use nu now. So we have nu1 and nu2, so that's our eigenvector is equal to the 0 vector. So we have 2, 2, 2, 2, nu1, nu2 is equal to 0, 0. And so we have 2 times nu1 plus 2 times nu2 equals 0. So 2 nu1, 2 nu2, I'll say nu2 is equal to negative nu1. And so plugging in, we say let nu2 equal, or nu1 equal 1, nu2 is equal to -1, and so our nu for lambda 1 is going to be 1, -1. So that's that. So now we'll have to plug in for lambda 2 equals 3. So we have this matrix. We have 1 minus 3, 2, 2, 1 minus 3. And then we have nu1, nu2 equals 0 vector. I'm just going to solve that. So we have nu2 equals nu1. Just you do the same process and solve for that. And so we let nu1 equal 1, nu2 equals 2. And so our nu vector, or our eigenvector 2, so for lambda 2 is 1, 1. So now we have those, we can plug in our general solution. And it's just like, you know, the differential equations that we solved this whole semester, or the summer session 1, I guess. We have x of t, this is matrix solution, is c1 e to the, now lambda is lambda t, so it's negative t, and then our solution up here. So we have -1, or 1, -1, plus c2 e to the, and then we have our second lambda, which is 3 t, and then our second eigenvector 1, 1. So that's our solution.